The North American industrial economy relies on a single physical choke point at Sault Ste. Marie, Michigan. The Poe Lock handles over 70% of all cargo transiting the Great Lakes system. This single chamber averages 40 million gross tons of iron ore and coal annually. Only the Poe Lock can accommodate the 1,000-foot superlakers. These vessels carry 70,000 tons of taconite per transit. Alternative rail and truck networks can absorb less than 10% of this daily volume. The physical channel is entirely irreplaceable in the short term. A structural failure of the Poe Lock would trigger an immediate industrial shutdown. Department of Homeland Security modeling shows integrated steel mills lose 35% of capacity within 2 weeks. By week 12, automotive assembly capacity drops to 15% as specialized steel inventories deplete. The total economic damage of a 6-month outage exceeds $1.1 trillion. Domestic manufacturing cannot substitute this iron ore with foreign imports. Deepwater port and rail constraints prevent rapid supply chain realignment. Mitigating this single point of failure requires building a second Poe-sized lock. However, the new Sault Lock project is severely delayed and over budget. Authorized costs escalated from $1.03 billion in 2020 to over $3.2 billion. Labor shortages and marine construction inflation have pushed the operational date to late 2030. The North American industrial core remains exposed to catastrophic failure for the remainder of the decade. Until completion, the continent's steel supply chain operates on a razor-thin margin of safety. The Paraná-Paraguay Hidrovía is experiencing an unprecedented hydrological crisis. Severe drought in the Pantanal wetlands has reduced the river draft at Asuncion to a historic low of 5.5 meters. This represents a 47.6% decline from the 2019 baseline. Barge operators must reduce cargo loads to avoid grounding in the shallow channels. Convoys are running at just 58% capacity. This inefficiency requires 1.7 times more trips to move the same volume. Freight surcharges have consequently surged to $15.50 per ton. Exporters are bypassing the degraded river system by shifting to overland trucking. Trucking bulk commodities to the Brazilian port of Paraná costs $85 per ton. This is a 286% cost premium over normal river logistics. Low drafts and new transit tolls have pushed river costs to $38 per ton. While trucking cuts transit times to under 5 days, it presents a severe environmental penalty. Carbon emissions increase by over 350% compared to water transport. The regional logistics network is trading structural efficiency for basic operational survival. Geopolitical friction is compounding the physical bottleneck. Argentina's unilateral transit toll of $1.47 per ton generated over $18 million in 2024. This levy has strained relations with Paraguay and Brazil without resolving the infrastructure deficit. Dredging operations are failing to keep pace with rapid siltation. The dredging deficit reached a record 3.6 million cubic meters in 2024. Uncompleted work has left channels dangerously shallow. As a result, annual demurrage costs for stranded barges have peaked at $58 million. Advanced semiconductor manufacturing relies on an extremely concentrated chemical supply chain. China controls over 90% of global refining capacity for high-purity yttrium oxide. This material is critical for protecting the internal chambers of plasma etching systems. The United States and its allies maintain less than 3% of domestic refining capacity. Alternative processing sites in Japan and South Korea are not independent. They depend entirely on unrefined yttrium concentrates sourced from Chinese mines. This creates an absolute single point of failure at the raw material level. As fabrication nodes shrink below 5 nanometers, chamber survivability dictates chip yields. Standard quartz and alumina components erode rapidly under highly corrosive fluorinated plasmas. This erosion generates microparticles that ruin silicon wafers during the etching process. High-purity yttrium oxide coatings reduce erosion to just 1.8 nanometers per minute. This represents a 98.5% reduction in wear compared to quartz. Particle generation drops from 450 particles per hour to under 4. No other commercially viable material matches this level of plasma resistance. Expansion of sub-3 nanometer fabrication facilities is driving an acute supply deficit. Global demand for semiconductor-grade yttria will reach 3,700 metric tons by 2026. This demand has already surpassed total non-Chinese refining capacity. Western and East Asian fabrication plants are highly exposed to Chinese export quotas. These quotas are inelastic, capping exports at less than 1,800 metric tons annually. The mismatch forces a direct reliance on Chinese domestic production to sustain advanced chip manufacturing. Without rapid alternative supply chain development, advanced fabrication lines face severe operational limits. South Africa holds over 70% of the world's viable chrome reserves. Historically, state-owned rail moved this critical mineral to domestic ports. The systemic collapse of Transnet freight rail has forced a complete structural inversion of these logistics. Mining companies now bypass domestic rail entirely, routing bulk ore by road to neighboring Mozambique. Rail-bound chrome exports declined by over 60% in 5 years. Conversely, road-bound exports through the port of Maputo expanded by nearly 400%. By 2023, this single road corridor handled over 62% of South Africa's chrome exports. A foreign port has become the primary logistical outlet for the Bushveld igneous complex. The physical driver of this shift is the decay of South Africa's locomotive fleet. Active locomotives on the northeastern chrome corridor fell from 120 to just 42. Maintenance backlogs and procurement disputes have paralyzed the rail network. This has forced a massive migration of bulk cargo to the highway system. Daily heavy truck crossings at the Mozambique border scaled from 350 to 1,600. This surge has created border processing delays of up to 36 hours. It has also driven the road transport cost premium to $44 per ton. South African mining operators are paying a severe structural tax to keep material moving. The logistics crisis has now accumulated at the receiving port. In 2023, chrome throughput at the port of Maputo exceeded its nominal terminal capacity. The port was not engineered to handle such high-intensity, truck-delivered volumes. This mismatch has triggered severe maritime congestion. Average vessel turnaround times have risen from 3.2 days to 18.5 days. This represents a 478% increase in port dwell times. Daily demurrage penalties for waiting bulk carriers averaged $45,000 in 2023. The physical limits of Mozambican infrastructure now form a secondary bottleneck for global stainless steel supply chains. Advanced semiconductor manufacturing is fundamentally constrained by the geology of the Bushveld igneous complex. South Africa controls an average of 78.9% of global ruthenium supply. This extreme geographic concentration exposes the entire lithography supply chain to Eskom grid instability. Ruthenium cannot be mined directly. It is recovered exclusively as a low-yield byproduct of platinum and nickel extraction. Consequently, the global supply profile is highly inelastic and cannot scale to meet rising industrial demand. In 2024, global output contracted to an estimated 795,000 troy ounces. This represents a 6.47% decline from the 2021 peak. Capital expenditure cuts in primary South African shafts continue to suppress yields. Severe demand shock is reshaping the ruthenium market. Extreme ultraviolet lithography applications are growing at a compound annual rate of 44.2%. This rapid expansion is driven by the industry transition to high numerical aperture systems. By 2026, lithography capping layers will consume over 22% of global supply. This is up from just 2.1% in 2019. The semiconductor sector is actively cannibalizing material from legacy, chemical, and electrical industries. This structural shift points to an imminent market deficit. By 2026, demand is modeled to outpace flat supply by 80,000 troy ounces. Without commercial-scale recycling breakthroughs, this deficit will directly bottleneck advanced chip fabrication. The physical scaling of advanced lithography has permanently altered ruthenium market dynamics. In 2021, average prices spiked by over 132% to $650 per ounce. This surge directly correlated with a rapid acceleration in extreme ultraviolet system shipments. The physical requirements of next-generation systems explain this price pressure. Standard systems require 15 to 20 grams of high-purity ruthenium per mirror array. High numerical aperture systems require up to 45 grams to withstand intense source degradation. The post-spike price floor has stabilized above $450 per ounce. This represents a permanent structural step-up of over 100% from the 2018 baseline. Chip makers exhibit highly price inelastic behavior, prioritizing material security over cost. China's energy grid is undergoing the most capital-intensive expansion in electrical history. The state grid has built over 95,000 kilometers of ultra-high voltage lines. This physical network has expanded by 220% since 2016. Total transmission capacity now stands at 510 gigawatts. This infrastructure bridges the multi-thousand-kilometer gap between Western resources and Eastern demand. The capital expenditure for this build-out exceeds 1.25 trillion renminbi. This equates to over $173 billion. The system now forms the physical backbone of the national energy strategy. Severe spatial mismatch defines China's macroeconomic geography. The industrialized East Coast experienced a structural electricity deficit of 1,100 terawatt-hours in 2023. Manufacturing centers cannot survive without importing massive quantities of power from the interior. The western and northern provinces generate the necessary surplus. The northwest provinces produced a net surplus of 440 terawatt-hours. This power is generated by massive solar and wind installations in the Gobi Desert. Southwest China provides another 370 terawatt-hours of surplus. However, this hydropower remains highly seasonal and fluctuates by up to 45%. The transmission of clean energy introduces a severe technical paradox. Intermittent wind and solar power risk causing grid collapse at eastern receiving terminals. To stabilize these corridors, operators must co-locate massive coal-fired plants at the sending nodes. Coal remains the largest single component of transmitted energy at 410 terawatt-hours. This represents over 43.2% of the total transmitted power. Wind and solar transmission grew at a compound annual rate of 30.1% from 2018 to 2024. Yet this green energy remains structurally dependent on continuous coal combustion. Hydropower has stabilized at 250 terawatt-hours as major basins reach maximum exploitation. Deepwater oil and gas extraction depends on a highly concentrated mineral supply chain. Barium sulfate, or barite, is the primary weighting agent used to maintain hydrostatic control in high-pressure wells. 3 nations, China, India, and Morocco, control over 71% of global supply. This concentration exposes global drilling operations to localized regulatory shocks. Strict environmental enforcement in China's Guizhou province triggered a sharp contraction in output. Chinese barite production fell 28.5% between 2021 and 2023. This supply squeeze directly threatens the United States offshore sector. The United States imports approximately 75% of its barite demand. The Gulf of Mexico deepwater fleet alone consumes over 1,200,000 metric tons annually. The contraction in high-grade supply has driven a rapid escalation in landed costs. At the United States Gulf Coast, import prices for premium 4.20 specific gravity barite nearly doubled. Landed costs rose from $145 per ton in 2019 to $280 in 2024. This supply shock has widened the quality premium for high-density material. The price spread between premium and low-grade barite expanded by 183%. This spread now stands at $85 per ton. Logistical bottlenecks compound these material costs. Ocean freight from India and Morocco represents up to 55% of the total landed cost. Exporters face a compounding crisis of rising mine gate prices and volatile bulk shipping rates. This supply deficit coincides with an unprecedented surge in deepwater exploration. Active deepwater rigs in the Americas rose 81.5% since 2020. This expansion has pushed the annual high-gravity barite deficit to 550,000 metric tons. To bypass this shortage, operators are forced to accept lower-grade 4.10 specific gravity material. This substitution introduces severe downhole engineering risks. Achieving equivalent mud weights requires a higher volume fraction of suspended solids. This adjustment increases plastic viscosity by up to 18%. The resulting pressure spikes elevate the risk of induced formation fractures and lost circulation. In narrow-margin deepwater wells, saving on material quality increases the probability of a catastrophic blowout. Advanced semiconductor manufacturing nodes require extreme radio frequency power densities. Under these conditions, traditional single-crystal silicon focus rings erode rapidly. At the 3 nanometer node, silicon rings degrade within 65 hours. This degradation forces frequent tool shutdowns and compromises edge wafer yields. Transitioning to polycrystalline silicon carbide focus rings resolves this physical limitation. The material's high covalent bond energy resists halogen plasma sputtering. This extends operational lifetimes to 480 hours under identical conditions. At the 2 nanometer node, silicon ring lifetime drops to 40 hours, rendering it entirely non-viable. The transition to silicon carbide has created a structural supply deficit. In 2022, global demand outstripped maximum chemical vapor deposition capacity. This deficit is projected to widen to 110,000 units by 2026. The bottleneck is driven by the slow physical scaling of specialized reactors. Synthesizing polycrystalline silicon carbide requires temperatures exceeding 1,300 degrees Celsius. The vacuum chambers have lead times of 14 to 18 months. Furthermore, the supplier base is highly consolidated. Just 3 firms control over 75% of global output, leaving advanced fabrication lines highly vulnerable. Economic justification for this material transition is decisive. Silicon carbide focus rings carry a 48.2% higher annual consumable cost. However, they reduce annual chamber downtime from 438 hours to just 73 hours. This represents an 83.3% reduction in maintenance overhead. Edge wafer yield loss also drops from 1.45% to 0.22%. The spatial stability of the plasma sheath prevents edge defects over extended production runs. Consequently, the net annual operating cost per etcher is over 40% lower. Advanced fabs must secure these consumables to maintain both physical yields and financial viability.